So, we will continue discussion on crystal diffraction by X-ray. So, in last class we have seen that Bragg's treatment it is based on model reflection model. So, Bragg considered that X-ray will fall on the crystal and crystal will diffract, X-ray will diffract from the crystal. Now, it diffracts in different angles. So, that diffracted rays basically they interfere with each other, okay, and we get constructive interference, destructive interference. So, we get the basically the fringe, right. So, this that fringe is we generally express in terms of peaks, right. So, that I have shown you in case of grating. So, in Bragg treatment, considering the Bragg treatment, what we derived that condition for diffraction 2d sin theta equal to n lambda. So, what is d? D is the basically lattice spacing. So, these are parallel planes is the lattice spacing and theta is the gauging incidence angle, okay, with the plane. So, this diffracted, so when X-ray falls on these planes on this crystal, so then it will be diffracted. So, it will be diffracted in different angles. So, then diffracted rays interfere and we get the interference effect, variation of the intensity due to interference. Okay. So, these diffracted rays is basically we will get in different direction, and we will get constructive destructive interference. Okay. So, this here Bragg select those diffracted rays which follows the reflection rule and assume that those reflected rays will interfere constantly. So, they picked up the right set of diffracted rays which will interfere and give the constructive interference. Okay. So, among many diffracted rays, so they picked up those rays which are basically equivalent to reflected rays and they interfere constructively. So, that is the assumption and give this relation where d is this lattice spacing, theta is gauging incidence angle and lambda is the wavelength of this X-ray, right. N is the order of the interference. Okay. So, you are familiar with the order, first order, second order, third order interference maxima, right. So, this so from here what we will get? So, this will get like just as for getting what we got this this principal maxima. So, here this same so here if it's angle. So, at different angle, so I will not draw this one first. So, if it is say instead of in middle, let me. So, this is the 0 degree. If I take this the 0 degree. So, now for a particular d, and if X-ray wavelength is also monochromatic, and if we choose a particular lambda. So, say you are taking copper from copper target, copper K alpha X-ray, its wavelength is 1.54 angstrom, right, and say you are taking a particular d. So, if it is 100 planes, is h scale 100, h scale 100. So, then these planes will be d 100, okay. Then sin theta equal to n lambda. So, lambda is constant. So, these also for a particular planes. So, these also constant. Now, when this equation, this relation will be satisfied, then we will get the peak, that is constructive interference, that peak will get. So, what we will do, this we will vary theta, we will just change this angle. How to change angle, I will discuss. So, we have to change the angle, and then for a particular angle, this relation will be satisfied. So, this relation will be satisfied for a n equal to 1 first order, for n equal to 1 say first order, okay. And then if we continue to continue the change of angle, so we will get the second peak, we will get the second peak, we will get the second peak, we will get the third peak, right. Okay. So, this peak is for n equal to 1, n equal to 2, n equal to 3. So, first order, second order, third order peak, right. And this angle, it depends on lambda. So, lambda we have fixed it, it will depend on this d value. So, that also we have fixed. So, this corresponding will get theta. So, that theta basically for this plane, here we will get for second order peak, third order peak. So, it is there. If I scan this whole angle, so I will get for a particular plane, I will get the diffraction peak or interference peak, so at different angle, fine. Now you see this, if we consider n equal to 1, only if we consider the first order peak, then so from the beginning we will put n equal to 1, 2d sin theta equal to lambda. So, we will consider only first order peak, because second, third order peak is not giving me any additional information, right. So, we can consider any one peak and corresponding angle we can put here, right, for that order. So, we can take any one order. So, generally we take first order. So, all the time we use this n equal to 1. Okay. But one has to be careful, sometimes what happens for second order peak also appears. So, that I will discuss. So, here, so this it is not the only one plane in crystal. So, because I have a, this is a crystal and this is not only one plane. So, this is a one plane which is equivalent to a set of parallel planes. So, if it is 1 0 0, say 1 0 0, so then there are other 1 1 0, 1 1 1, 2 0 3, there are 100 and 100, 1000 and 1000 planes are there. Okay. So, X-ray is falling, I am changing the angle. So, when, so it will reflect from a particular plane, it will reflect from a particular set of plane having a d lattice spacing. So, satisfying this relation, so for a particular angle I will get the peak, right. So, simultaneously what happens here, another set of planes are there, already there, another set of planes are there. So, this X-ray it is falling on all planes, all set of planes, okay, having different h scale. So, this X-ray is falling on this plane and getting reflected, right. So, this X-ray will fall on this plane also, right, and now you can see this for this plane. So, this angle is different, earlier this angle, now for this plane this angle are different, right. So, following the reflection rules it will be reflected, right, it will be reflected having the same, right. So, similarly from these sets of plane we will get reflected rays, right. So, this spacing is, say now this spacing is, so say this is d11 d1, so this spacing is d2, right. So, when I am changing the angle, so it is this X-ray, incident X-ray is changing angle with all planes, right. So, from these sets of plane for d1 constant, lattice constant, lattice spacing. So, from this plane I will get peak at a particular angle when it will satisfy this relation, right. So, say this is the peak first order I am getting, and from these sets of plane lattice spacing d2 I will get the peak first order peak for these sets of plane at different angle which will satisfy this relation. So, say I am getting here, okay. So, you may consider another sets of planes. So, this which way I can, there may be another sets of planes. So, I think I have to in between okay. So, another set. So, it is said the spacing is d3, the spacing is d3, right. So, continuously we are changing the angle, and then from all planes this X-ray are diffracted, right. So, depending on the d value, so this relation will be satisfied because lambda is constant, this relation will be satisfied at different theta. So, when at that theta we will get peak for a particular d value, right. So, this way we will get enormous many number of peaks, which will for first order, which will basically the peak for a particular, each peak for a particular plane. So, say I will get the third plane, this third peak for D3. So, this is for D1, this is for D2 n equal to 1, this is for D3 n equal to 1, right. So, here we will get many first order peaks, each peak will basically indicating a set of planes, a set of parallel planes, H-scale plane. Okay. So, but here one has to be just careful, here just I have drawn different order, generally we consider the first order only, but one has to consider that okay, at a higher angle sometimes this N2 second order may come, second order peak may come. So, we should not confuse with the whether it has come from different plane or it has come from same plane, but it is second order. So, that one has to be careful when analyze this X-ray data. So, that is so using this relation we can get peak, and each peak will correspond to a particular plane. So, I am just considering that only first order peak. So, I will not mention, if necessary then I will mention for other order, otherwise you may consider that only I am talking about the first order peak. So, we will get different peaks which corresponds to different planes. Okay. So, from that scan experimentally what you are getting? You are getting different peak, So, basically experimentally we are measuring the angle, diffraction angle or reflection angle, whatever, we are measuring the angle, and this lambda is known, we are measuring the angle theta, right. So, this from this relation then you will get d value, so that is lambda by 2 sin theta, right. So, I will get the lattice spacing d value. Now, d is related with the lattice constant. So, let us consider only simple cube. Okay. It is then it will be easy to understand. So, we know the relation between the lattice parameter, lattice constant and the lattice spacing. So, what was that relation? So, it was basically 1 by h by a whole square plus a by b whole square plus L by C whole square, this square root. So, it is under square root. Okay. So, that was the relation between the lattice parameters and this. So, for cubic system, so d equal to say a equal to b equal to c. So, d equal to basically a by square root of a square plus a square plus l square, right. So, from this relation one can find out the lattice constant, right. A value for cubic system A value, for other system also orthorhombic or tetragonal, yes. So, one can find A, B, C value. So, for that so you need so you have to analyze the data properly to get, because here you have to know the H scale value, right. So, this D for, so D just here D I will get, but from it is which plane that I do not know, H scale also unknown to me. Okay. So, one has to get the lattice parameter. So, one has to know the H scale value. So, that there is a way to analyze and find out this lattice parameter. So, that I will discuss later on. So, now just here I try to tell you that using this simple relation that is called Bragg, that is called Bragg's law. That is called Bragg's law, and Bragg's law, in case of Bragg's law, diffraction and reflection, diffraction and reflection, these two terms are used are frequently used, but both are having the same meaning. Okay. So, they are interchangeable. So, in case of Bragg's law, generally we use the reflection term, not diffraction term, but basically it is diffraction term. So, these both terms are used in same sense. So, we tell this Bragg reflection instead in place of Bragg diffraction. Okay. So, why it is diffraction basically, but it is a reflection that as I mentioned this, they have considered the constructive interference only, where we will get the peaks, okay, and those diffracted rays which follow the reflection rule and they interfere constructively. So, that is why these two terms are equivalent in case of Bragg treatment. Okay. And from there, this in simple, these relations are there, this D one can find out experimentally measuring the angle theta, Bragg angle, these are called Bragg angle. Okay. And then this D is related with the lattice parameters. Okay. So, one can find out the lattice parameter. For that one has to know the Miller indices of this plane. So, we will have many planes. Okay. So, these different planes have different Miller indices, right. So, one has to analyze in proper way to get this A knowing this Miller indices. So, that will be discussed during analyze the data. I think I will discuss. So, now what happens? So, here just theoretically I told, okay, so this way theoretically I told that this way if one can find out the lattice parameter, but for that you need the experimental arrangement. So, there are basically three experimental arrangement. So, for all experimental arrangement, this is the parent relation, Bragg's law. Okay. Based on this relation, this law, so there are three experimental arrangement. So, that I will mention. So, I have basically 2d sin theta equal to lambda. So, this is the this is the Bragg law, Bragg equation. Okay. Now, we will get whatever we will get, that for that this relation has to be satisfied. So, we have 3 parameter basically here, one is d, one is theta, another is lambda. Our aim is to find out this d, right, and d again related with the lattice constant, right, a, b, c, etc., right. So, this variable, mainly these two are, one has to vary, or one can be taken constant, other one can be varied. So, one variable is must, because this to satisfy this condition there has to be one variable, minimum one variable, right. So, experimentally, so this there are, as I told, there are three method experimental arrangement. So, one is called this Laue method, one is called Laue method. So, in case of Laue method, theta is fixed, but lambda varies. So, basically white X-ray is taken, where all lambdas are there, right. So, I have shown you this type of X-ray spectra, right. So, this is the lambda. So, all sorts of wavelengths are there. So, white light. So, lambda is variable here. In this method, lambda is variable. So, theta is fixed. Now, theta is fixed, yes, and now lambda is variable. So, d depending on d, okay, lambda is, so lambda will vary to satisfy this relation. Okay. The sin theta is having a fixed value. Now, for different d in crystal, what is there? Different d are there, right? Different sets of planes are there. Okay. So, to satisfy this one for d1, d2, d3, whatever, for each set of planes, for each set of parallel planes, for a particular d value. So, it has chance to pick up the right lambda to satisfy this one. Okay. For another sets of plane, for d2 say, so it will pick up the another lambda to satisfy this relation. Okay. So, we will get peaks or constructive interference for all planes in crystal. Okay. So, this is the Laue method, and second method is called rotating crystal method. So, rotating crystal means X-ray is falling on the crystal. Now, crystal is rotating, so its plane, so angle with these planes are changing. So, in this case, theta is variable. Okay. So, other one can be constant, lambda is constant, means monochromatic X-ray is used. So, this is monochromatic. So, it is monochromatic X-ray. So, generally this K alpha, it has maximum intensity. So, that is generally is filtered from this white X-ray and used for this as a monochromatic X-ray. Okay. So, in this case, so crystal this is rotating with respect to this incident X-ray. So, now now crystal is rotating, this is the incident X-ray. So, angle with the planes will change. So, theta will vary, okay. Lambda is constant. Now, for different d, so theta is available, okay. So, it will pick up a particular theta for a particular planes, okay. So, I will get again just due to the variation of this angle. So, it will at different angle for different planes, this relation will be satisfied. So, I will get again many peaks, okay. So, third one is called powder method. Third one is called powder method, okay. So, powder method means both these two are for single crystal. I think it is I will. So, it's for single crystal. Whether I can show this. So, this is a silicon crystal. So, we tell this wafer. So, generally this 3 inch 4 inch diameter silicon wafer is available. So, this is a one piece of that silicon crystal. So, single crystal means this type of crystal, this type of crystal of different metals are used, this type of metals are used, okay. And these are the basically heart of electronics instrument, you know. Different materials are deposited on this crystal and fabricated the IC, different electronic circuit. So, just here I want to just show that these crystals are this type, this is silicon crystal, you have germanium crystal, gallium arsenide crystal, sodium chloride crystal. So, this is just one, okay. This is single crystalline. Now, if I break this one and make very small piece in micrometer order, so few of this, each particle will be of few millimeter, few micrometer. So, then we tell it is a powder, okay. So, its best example is the sodium chloride, this salt. We take salt, right, in our with our food. So, this just I have taken salt. So, this nothing but is it's sodium chloride crystal. If you bake it and make many pieces like this, okay. So, then we tell this is a powder form of the crystal, okay. So, what does it mean? So, each particle or each piece is a single crystalline, okay. So, now we have many single crystalline particles together. Now, these single crystalline particles have all sorts of plane, right. So, now if you consider 1 0 0 plane, so in one particle these planes are there, right. In another particle these planes also there. So, in all particles these planes are there. Now, in which direction they are oriented, So, that is the main importance factor for powder method. So, we can tell that if X-ray is falling on this, so 1 0 0 plane for a particle, it is making angle say some angle say 5 degree. So, then another particle that same planes will make angle 5.5, 5.9 etc. So, you can assume that for this powder crystal X-ray will make angle from 0 to 180 with for a particular plane. Okay. So, each plane will have all 0 to 80 all angles, continuous change of angles for this powder method. Okay. So, so this is the basically what I want to tell, this is the powder, and this in this method we are using basically this type of powder crystal, where angle, incident angle of X-ray for different planes are continuously variable. So, in this case this angle is variable, So, it is not, we are not rotating, but using the powder. So, we are getting this variation, variable, and lambda is fixed, constant. So, this basically this lambda X-ray is monochromatic. Okay. So, here also we have theta variable, lambda is constant. So, usually this crystal this relation will be satisfied for different planes at different angles. So, we will get again many Bragg peaks, okay, and from that Bragg peaks we can basically get different d, and then different d will be related with the lattice parameter, and one can find out the lattice constant. Okay. So, that we will continue discussion on this topic. So, thank you.